Yeah, I found a new dance partner. This is Daisy.
There's no one there.
That's a bit rude. Yeah. Daisy's a bit offended that you called her nobody.
Don't see insane. There's nobody there. Look. No one. I can't see a Daisy. I can't touch a Daisy. I can't hear a Daisy. She doesn't exist.
Well, actually, just because we can't see something, hear it, smell it, does that mean it doesn't exist? Physics says otherwise. Our universe has 10 to the 23 stars. Some of these stars have planets, and there is dust in the universe. There is matter everywhere. But even if we had all the observable matter, there is still matter missing. So, what is this missing matter? Dark matter.
Matter. Atoms, stars, galaxies, planets, and us accounts for only 5% of the known universe. The rest of our universe is a combination of dark energy, approximately 68%, and dark matter, around 27%. And these are completely invisible. They simply do not interact with any electromagnetic radiation, so are undetectable to us. To prove that Daisy truly exists, we'll focus on dark matter. We know that dark matter exists because the universe appears to have more mass than can be accounted for by ordinary visible matter. So, what is dark matter? We can tell you what it isn't. It was thought that dark matter was actually just the gravitational effects of massive compact alien objects, also known as machos. These are relatively small objects but with high masses and densities, such as brown dwarfs, black holes, or neutron stars. Since these objects do not emit light, they are essentially invisible, so they are the perfect candidates, right? Black holes and neutron stars require supernovae, and these are not common occurrences. So we haven't found enough neutron stars and black holes to account for the missing matter. Brown dwarfs, however, do not require supernovae, and while these have been discovered, experimental evidence suggests, again, there are too few brown dwarfs to account for all the dark matter in our galaxy, so they're out. We can also say with certainty that it is not antimatter, as there are no observations of the gamma rays that we'd expect to be produced upon annihilation. The current theories on dark matter suggest that the missing matter must be due to WIMPs. By WIMPs, I mean weakly interacting massive particles. These are subatomic particles, able to pass through ordinary matter without interacting with it, even though they have mass. These particles are theoretically possible according to our standard model. At the moment of the Big Bang, there might have been WIMP particles created in ideal amounts with ideal mass needed to explain the invisible matter in our galaxy. So if dark matter is invisible, how do we know it's even there? Well, there are several telltale signs. Back in 1933, Swiss astronomer Fritz Zwicky first made the observations that the velocity at which some galaxies were spinning was so high that they should not be able to hold on to the stars within them. Later, in 1962, American astronomer Vera Rubin came to similar conclusions. Unfortunately, neither of these scientists were taken seriously. But now we know they must have been correct, and something must have been there to provide enough mass in order to hold these galaxies together. The most quantitative piece of evidence we have for dark matter is to do with rotational velocities of stars within galaxies, and even galaxy clusters themselves. Furthermore, for clusters of galaxies orbiting each other, the same phenomenon can be observed. This means that there must be some extra mass that is not being observed by measurements. This extra mass is dark matter. Further evidence for the existence of dark matter is observed by gravitational lensing. This is a technique used in astronomy for looking behind high-mass objects like galaxy clusters. where matter is highly concentrated, it is able to bend light. But when some of our lensed images are analyzed, the required bending mass is higher than our observed mass of the cluster. However, there are not enough lensing events occurring for us to come to any definitive conclusions about the presence of dark matter. Our final piece of evidence is the cosmic microwave background radiation. The CMBR is a radiation released from the Big Bang 13.8 billion years ago that has now cooled down and stretched into the microwave spectrum. This fossil radiation is not homogeneous. There are cold spots and hot spots. The hot spots correspond to where first dark matter and then visible matter started forming into lumps, providing the seeds necessary for galaxies. Nowadays, most scientists believe that dark matter is essential for the formation of galaxies.